Reinforcement learning, RL, is a branch of machine learning that focuses on training agents to make decisions in an environment to maximize a reward signal. Despite its growing popularity and success in various applications, RL can be challenging for beginners due to its unique setting, jargon, and complex mathematics. This paper provides a comprehensive overview of the key concepts, techniques, and algorithms for beginners, covering the general pipeline of an RL setting, technical terms, and the historical progress of the field from the early Q-learning algorithm to current state-of-the-art algorithms such as TD3 and PPO. The general pipeline of an RL setting involves an agent interacting with an environment, receiving feedback in the form of a reward signal, and updating its policy based on this feedback to maximize the long-term reward. The agent must explore the environment and try different actions to learn which actions lead to higher rewards, while also exploiting its current knowledge by taking actions expected to lead to the highest reward based on its current policy. This balance between exploration and exploitation is a key challenge in RL. Technical terms include the environment, which receives the agent's action and changes its state accordingly, and the policy, which refers to the sequence of actions executed by the agent given the corresponding environment states. All RL and deep RL algorithms must ensure an optimal balance between exploration and exploitation, a concept that is particularly associated with RL. The paper traces the historical progress of the field, starting with the early Q-learning algorithm until current state-of-the-art algorithms such as TD3 and PPO. The presentation of the paper is aligned with the historical progress of the field, providing a clear and concise introduction to the key concepts and techniques of RL, as well as a survey of the main algorithms that have been developed over the years. This paper aims to serve as a valuable resource for beginners looking to construct a solid understanding of the fundamentals of RL and be aware of the historical progress of the field. In the context of reinforcement learning, an agent learns to make optimal decisions by balancing exploration and exploitation. This is crucial because, if the agent starts exploiting a learned policy from the beginning, it may miss other policies with higher optimality. The Markov decision process, MDP, framework gathers these components as S, A, T, R, gamma, where S is the state, A is the action, T is the transition function, R is the reward function, and gamma is the discount factor. The discount factor determines how much the agent cares about rewards in the immediate future compared to those in the distant future. The agent generates an action at state street, changing the environment's state to Saint +1 and associated reward RT +1. The cumulated sum of rewards is the return GT, calculated as the sum of discounted rewards. GT equals RT +1 plus gamma, 1, RT +2 plus gamma, 2, RT +3 plus. The discount factor ensures mathematical convergence and models the importance of future rewards relative to immediate ones. To make the setting more suitable for real-case scenarios, the expected return of GT, also called the value function VT, is considered. VT equals east, GT, street equals S. Solving the MDP consists of maximizing the value function. However, this is a difficult problem, known as the infinite horizon problem. To address this, the Bellman equation trick is introduced, which recursively approximates the return G and the value V. VT equals RT +1 plus VT +1. Based on these concepts, various algorithms and techniques have been proposed to solve reinforcement learning problems. Table 1 presents a taxonomy of foundational RL and deep RL algorithms, including Q-learning, DQN, reinforce, DDPG, TD3, and PPO. These algorithms are categorized as value-based, policy-based, model-based, or model-free, and can be on-policy or off-policy. The following section will present each algorithm in detail, including their motivation, inner workings, and limitations. The Q-learning algorithm is a TDBASED model that belongs to the tabular RL model family. It updates the model's policy based on the value function V and does not require a model of the environment. Other algorithms, such as Sarsa and Monte Carlo tree search, will also be discussed. These algorithms are either TDBASED or Monte Carlo based, and rarely rely on dynamic programming. Q-learning is a fundamental algorithm in reinforcement learning, introduced by Christopher Watkins in 1989. It considers a Q function, which evaluates the quality of a state-action pair, as opposed to the value function V, which only associates with states. The Q function is defined as the expected return when taking action A in state S and following policy Pi thereafter. The relationship between V and Q is formulated as the mathematical expectation of Q over all possible actions. Q-learning uses a Q-table to store the Q-value of taking a certain action in a given state and updates it based on the observed reward and estimated future value. The update rule is given by equation 7, where alpha is the learning rate, and gamma is the discount factor. The algorithm iteratively updates the Q-table using the epsilon-greedy method, which ensures exploration and exploitation. Algorithm 1 outlines the Q-learning procedure, which initializes the Q-table arbitrarily and repeats for each episode. At each step, the algorithm chooses an action using the policy derived from Q, takes the action, observes the reward and next state, and updates the Q-table. The process continues until the terminal state is reached. However, Q-learning has limitations, particularly in environments with continuous states and actions. To address this, Deep Q-learning (DQN) was introduced, which uses function approximators, specifically neural networks, NNs, to store the Q-values. DQN has been successfully applied in various domains, including medicine, industrial control, and games. The DQN architecture involves two successive designs, with the second one improving upon the first. The original DQN replaced the Q-table with a NN, enabling gradient-based updates. However, this suffered from experience correlation and the moving target problem. The updated DQN architecture addressed these issues, and the paper has been widely cited, with over 9,500 citations. The inner workings of DQN involve a NN that learns to approximate the Q function, and the algorithm iteratively updates the network using the TD loss. The Q-learning algorithm has a fundamental limitation, as it uses finite-sized tables to store Q-values, making it inapplicable to environments with continuous states and actions. In contrast, DQN uses NNs to store Q-values, enabling its application to more complex domains. The Enhanced Deep Q Network (DQN) architecture is proposed to mitigate two significant problems: correlation between successive experiences and the moving target problem. This is achieved by introducing two main blocks: the replay memory and the target network. The replay memory stores transitions of state, action, reward, new state, until having batches, then randomly samples transitions for learning, ensuring independent, identical, and distributed, IID-like data. The target network, a separate network for calculating the target Q-value, makes the model more robust and stable. The inner workings of the DQN architecture are illustrated in Figure 3 and Algorithm 2. The learning episodes begin by initializing the two networks' parameters, and the agent gives an action based on the state provided, receiving a new state and reward from the environment. This transition is stored in the replay memory. After a couple of episodes, the stored transitions are sampled randomly to compute their corresponding Q-values. The Q network is updated via the mean square error, MSE, to minimize the loss between the predicted Q and the real one, while the target network's parameters are updated by copying the Q network's parameters. However, DQN has limitations, mainly due to the categorical way of generating actions, making it unsuitable for continuous action settings. Additionally, DQN shows significant training instability in high-dimensional environments, prone to overestimation error. In contrast, policy gradient (PG) algorithms, popularized by Sutton et al., propose a direct way of doing reinforcement learning with neural networks. Unlike value-based methods, PG algorithms have a solid mathematical basis, directly mapping states to actions via a learnable, differentiable function approximator. The gradient loss in PG algorithms is directly proportional to the policy, intuitively. The PG theorem proof is based on the mathematical expectation E, where the gradient of the objective function can be formulated as the integral of the probability of the trajectory and the reward. The policy gradient theorem is utilized to derive an expression for the gradient of the objective function, allowing for the direct update of the agent's parameters based on its policy. This is achieved by applying the log derivative trick, which transforms the expectation of the reward into a form that can be optimized using gradient ascent. The resulting expression, nabla theta j, pd, equals e, n array summation nabla theta log, pd, at, saint, r, tau, tt equals 0. Enables the training of reinforcement learning agents in continuous setting environments. The reinforce algorithm is a straightforward implementation of the policy gradient theorem, where a neural network is used to map states to actions optimally. The agent learns to choose actions that maximize the objective function via gradient ascent. However, the reinforce algorithm suffers from noisy estimates of the gradient due to unclear credit assignment, as the agent is only updated when a complete episode of data is completed. To address this limitation, actor-critic architectures were proposed, which utilize both the policy and value functions for learning optimal strategies. The actor is responsible for learning the policy, while the critic learns the value function or action value function. The advantage function, A, is calculated as the difference between the next estimated value and the previous one. The deep deterministic policy gradient (DDPG) algorithm is an actor-critic model that operates in high-dimensional continuous state and action spaces. It uses a deterministic policy function, mu, s, thm, to map states to actions directly. The critic learns by minimizing the mean squared error loss between the predicted Q value and the actual one. The actor and critic networks are updated simultaneously, allowing the agent to learn optimal policies in complex environments. The use of actor-critic architectures has become a standard approach in deep reinforcement learning, particularly in model-free settings. The combination of policy and value functions enables the agent to learn more effectively and efficiently, leading to state-of-the-art performance in various tasks. Here is a combined summary of pages 11 and 12 of the research paper. The deep deterministic policy gradient (DDPG) algorithm is an actor-critic model that combines the advantages of policy gradient methods and Q-learning. It uses a critic to predict the Q values and an actor to select actions. The critic is trained using a replay memory and target network, similar to the Deep Q network (DQN) model. The target network is updated using a soft copy based on the Polyak averaging function, which constrains the target network to change slowly and yields better performance. The action selection in DDPG is executed according to the equation at equals mu, street, thm, plus ent, where ent is a noise signal added to the policy function to force stochastic behavior. The Ornstein-Uhlenbeck noise is used, but later research has shown that other simple noise signals such as Gaussian noise can be used and yield competitive performance. The DDPG algorithm is presented in Algorithm 4, which initializes the critic and actor networks, target networks, and replay memory. The algorithm then iterates through episodes, selecting actions, executing them, storing transitions in the replay memory, and updating the critic and actor networks. However, DDPG has limitations, including instability and high sensitivity to hyperparameter tuning, which can lead to convergence to poor solutions or divergence in tasks requiring more exploration. To address these limitations, the twin-delayed deep deterministic (TD3) policy gradient model was developed. TD3 solves the overestimation bias issue in DDPG by maintaining a pair of critics, Q1 and Q2, along with a single actor. Each network has its own target network, and the minimum Q value is used to update the policy. This approach reduces the overestimation bias and improves the performance of the algorithm. The twin-delayed deep deterministic (TD3) policy gradient algorithm employs two critic networks to approximate the Q value, mitigating the overestimation bias inherent in Q-learning and deep Q networks (DQN). The TD3 model updates the policy less frequently than the critic networks, using the smaller of the two Q values. This approach is inspired by double Q-learning and double DQN, which also utilize two networks for improved Q-value approximation. The TD3 algorithm is similar to the deep deterministic policy gradient (DDPG) model in selecting actions and updating networks, as outlined in Algorithm 5. The TD3 algorithm initializes two critic networks, Q-theta1 and Q-theta2, and an actor network PIF, with target networks theta 1 foot and theta 2 feet and phi. The algorithm iteratively selects actions with exploration noise, observes rewards and new states, and stores transitions in a replay memory. A mini-batch of transitions is sampled, and the policy is updated using the deterministic policy gradient. The critics are updated using the clipped double Q-learning target, which combines the minimum of the two Q values. The target networks are updated using Polyak averaging. However, TD3 has limitations, including manual exploration through Gaussian noise and computational heaviness due to the use of 6 networks. Additionally, TD3 is only suitable for continuous space environments. In contrast, the Proximal Policy Optimization (PPO) algorithm uses a stochastic policy, inherently handling exploration automatically. PPO learns online, collecting mini batches of experience while interacting with the environment, and updates its policy using a trust region approach. This approach ensures that policy updates do not deviate too far from the previous policy, resulting in smoother training and less variance. The PPO model was developed for ease of implementation, sample efficiency, and ease of tuning, and has shown impressive performance compared to previous models. Here is a combined summary of pages 15 and 16. The Proximal Policy Optimization (PPO) algorithm is a key contribution to the field of reinforcement learning (RL). By clipping the ratio of the old policy and the new policy between a manageable interval, PPO helps to prevent the learning rate from going outside the trust region, making hyperparameter tuning less laborious compared to DDPG and TD3. The PPO algorithm replaces the log pth at saint in the policy gradient PG objective function with the ratio RT theta equals pth new pth old, clipping it between 1 epsilon and 1 plus epsilon, and maximizing it using gradient ascent. The PPO algorithm is outlined in algorithm 6, which initializes policy parameters theta 0 and value function parameters phi 0. It then collects a set of trajectories, computes rewards to go, and computes the advantage estimates. The policy is updated by maximizing the PPO clip objective, which involves computing the clipped surrogate loss. The value function is fitted via mean squared error, MSE, loss. Despite being a state-of-the-art algorithm, PPO's limitations are yet to be fully explored. It has been used to fine-tune the ChatGPT model and is still the main algorithm used at OpenAI. In conclusion, the choice of RL algorithm depends on the specific characteristics of the problem at hand and the trade-offs between sample efficiency, stability, and convergence speed. Model-based algorithms are more sample efficient but may be less robust, while value-based algorithms are widely used but may suffer from instability or divergence. Policy-based algorithms are generally more stable but may be slower to converge. This review aims to provide a comprehensive overview of RL, including its key concepts, techniques, and algorithms, as well as its challenges and limitations. Reinforcement learning has been widely applied in various fields, including games, healthcare, finance, robotics, and supply chain management. Research has demonstrated the effectiveness of reinforcement learning in these domains, with many surveys and reviews published in recent years. Crespo and Wickert, 3, applied reinforcement learning to games, while Xiao et al. 4, surveyed deep reinforcement learning in video games. Yu et al. 5, reviewed reinforcement learning in healthcare, and Gottsman et al. 6, provided guidelines for reinforcement learning in healthcare. Coronado et al. 7, surveyed reinforcement learning for intelligent healthcare applications. In finance, Hambly et al. 8, reviewed recent advances in reinforcement learning. Singh et al. 9, surveyed reinforcement learning in robotic applications, and Kober et al. 10, reviewed reinforcement learning in robotics. Nguyen and Le, 11, reviewed deep reinforcement learning for robot manipulation. Vasquez-Contelli and Nagy, 12, reviewed reinforcement learning for demand response, while Rolfe et al. 13, reviewed reinforcement learning algorithms and applications in supply chain management. Mannion et al. 14, experimentally reviewed reinforcement learning algorithms for adaptive traffic signal control. Masavi et al. 15, comprehensively reviewed deep reinforcement learning methods and applications in economics. Lee, 16, provided an overview of deep reinforcement learning, and Arukumaran et al. 17. Briefly surveyed deep reinforcement learning. Watkins, 18, introduced Q-learning, and MNIH et al. 19, applied deep reinforcement learning to play Atari games. Sutton et al. 20, developed policy gradient methods for reinforcement learning with function approximation. Lillicrap et al. 21, presented continuous control with deep reinforcement learning, and Fujimoto et al. 22, addressed function approximation error in actor-critic methods. Schulman et al. 23, developed proximal policy optimization algorithms, and Liu, 24, proved the convergence of Q-learning. Tobin et al. 25, reviewed deep learning in multimedia healthcare applications, and Chen et al. 26, improved deep QE networks for user-side battery energy storage charging and discharging strategy. Park et al. 27, developed a deep reinforcement learning-based DQN agent algorithm for visual object tracking, and Lee et al. 28, applied deep Q-learning for dynamic resource allocation. Van Hasselt et al. 29, introduced deep reinforcement learning with double Q-learning, and Konda and Tsitsiklis, 30, developed actor-critic algorithms. Mathuron et al. 32, analyzed the problem with DDPG, and Schulman et al. 33, developed trust region policy optimization. These studies demonstrate the wide range of applications and advancements in reinforcement learning, highlighting its potential for solving complex problems in various domains.